future of aviation. It is the quietest and the most fuel-efficient narrow-body aircraft in the sky. And for us, the passengers, it is a dream. Why? Because there are no middle seats. It's a 2+2 configuration. No more fighting for an armrest with a stranger. On paper, this plane is a masterpiece of Brazilian engineering. It was supposed to be the giant killer, the plane that would make Boeing and Airbus nervous. It consumes 17% less fuel than the previous generation and has the most advanced fly-by-wire system in its class. But here is the mystery. Airlines are not buying it. While Airbus is celebrating hundreds of orders for its rival, the A220, the Embraer E2 is struggling to find a home. In the world of aviation, being the best doesn't always mean you win. Sometimes you can build the perfect machine, but the market simply refuses to take it. How can a plane that is so right be so wrong? Today we are going deep into the numbers. We are looking at why this tech shark is becoming a headache for investors instead of a gold mine. It's a story of great engines, bad timing, and very expensive legal trap. But first, hit the like and subscribe button. This simple action is vital for me. Thank you very much. The engine course. Innovation versus reliability. To understand why the E2 is struggling, we have to look under the wings. This is the Pratt & Whitney GFT, the geared turbofan. It is a technical miracle, but for many airlines it has become a nightmare. Here is the simple science. In a normal jet engine, the fan and the turbine spin at the same speed. But in the GFT, there is a gearbox. This allows the big fan at the front to spin slower, while the turbine inside spins much faster. This makes the engine incredibly quiet and saves nearly 20% on fuel. For an airline, that sounds like a license to print money. But here is the catch. This technology is extremely complex. The gearbox and the new materials inside the engines are under massive heat and pressure. In the first years of operation, this engine started showing teething problems. We are talking about hardware failures, cooling issues, and parts that wear out much faster than expected. Normally, you fix a part and the plane flies again. But today, the global supply chain is broken. There aren't enough spare parts. Now let's look at the math. In the first year of a new aircraft's life, you expect it to be in the air 10 or 12 hours a day. But many E2 operators found their planes stuck on the ground for months, waiting for engine repairs. If we compare the E2 to the older E1 during their first years, the dispatch reliability, which is how often the plane is ready to fly on time, was significantly lower for the new model. Airlines hate uncertainty. When a CEO looks at the E2, they don't just see a fuel-efficient jet, they see a risk. They ask, will this plane fly tomorrow or will it sit in a hangar because of a broken gear? For many, the 20% fuel saving isn't worth a plane that cannot fly. The legal trap. How unions grounded a giant. But wait, if the engine is the only problem, Embraer could just fix it, right? Wrong. The biggest problem for the E2 is not mechanical. It is a legal trap called scope clauses. To understand this, we have to look at the United States, the biggest market for regional jets in the world. In the US, major airlines like United, Delta, and American don't fly their own small planes. Instead, they hire regional airlines to do it for them. But here is a very strict contrast between the big airlines and their pilot unions. This contrast is the scope clause. It says, you can use regional pilots, but only if the plane stays under a certain size and weight. There is one specific number that killed the E2. 76,000 pounds. That is the maximum takeoff weight, MTOW, allowed for regional jets in America. The older Embraer E175 fits this rule perfectly. It is the king of the US skies because it weighs exactly what the union allows. But the new E175 E2, because of those big heavy fuel-efficient engines and those advanced wings, It weighs nearly 89,000 pounds. It sounds crazy, doesn't it? Embraer built a plane that is better, cleaner and more quiet. But because of a piece of paper signed by lawyers and unions, it is too heavy to fly in the US. The unions refuse to change the weight limit. They want to protect the jobs of pilots who fly the bigger mainline jets. They fear that if they allow heavier regional planes, the big airlines will stop using large jets and replace them with smaller ones. Embraer made a massive gamble. They believed the rules would change by the time the E2 was ready. They were wrong. The rules stayed the same. And now the E175-E2, the most important version of the plane, has zero customers in the world's most profitable market. It is a tragedy of modern aviation. You can spend billions of dollars on engineering and create a masterpiece, but you can still be defeated by a single line of text in a legal contract. The shadow of Airbus, a David versus Goliath battle. Now imagine you are a CEO of a mid-sized airline. You need a new jet. You look at the Embraer E2, but then you look at its biggest rival, the Airbus A220. And this is where the shadow of the giant falls over Embraer. The A220 was not always an Airbus. It started as the Bombardier C Series, a brilliant plane from Canada. But Bombardier almost went bankrupt building it. Airbus stepped in and used its massive global power to turn it into a superstar. How does Airbus win? It's simple. They are a one-stop shop. Airbus has deep pockets and a huge family of aircraft. When they talk to an airline like JetBlue or Delta, they don't just sell one plane. They can say, if you buy 50 of our big A321s, we will give you a massive discount on 20 small A220s. Embraer cannot do this. They are a smaller independent company. They have to make a profit on every single jet they sell. They cannot play the same money game as the giant like Airbus. The numbers tell a painful story. Airbus has over 800 orders for the A220. Embraer? They have around 200 for the E2. In the business world, success creates more success. Airlines see everyone else buying the A220, so they feel it is a safer investment. But there is one more secret weapon Airbus has – the pilots. If an airline already flies the Airbus A320, the most popular plane in the world, it is much easier to train their pilots to the A220. It feels like a part of the same family. If they buy the Embraer, they have to build a completely new department for training and maintenance. For many airlines, even if the Embraer is a slightly better technical machine, the Airbus is the better business decision. Embraer is fighting a war against a company that has more money, more influence, and a bigger family. It is a fight that is almost impossible to win. Global survival. Looking for a new home. So, is the E2 dead? Not exactly. Since the US market is blocked by legal rules and Europe is dominated by Airbus, Embraer is looking at the rest of the world. In places like Brazil, India, and Southeast Asia, the scope clause doesn't exist. These regions have thousands of islands and growing cities that need a plane exactly like the E2. Something bigger than a small turboprop, but smaller and cheaper to run than a massive Boeing 737. But the most important test is happening right now, in Canada, with Porter Airlines. Porter is the hero of the E2 story. They didn't just buy a few planes, they ordered up to 100 of them. They are using the E2 to fly long distances, like Toronto to Los Angeles or Florida. Porter is essentially a living laboratory. If Porter can prove that the E2 is reliable, that the engines stay healthy, and that passengers love the 2+2 seating, other airlines will stop being afraid. Porter is the advertising face that Embraer desperately needs. If Porter succeeds, the E2 survives. If Porter struggles, E2 may stay a niche aircraft forever. However, Embraer is smart. They are already preparing a plan B. They know the E2 might never be a global bestseller like the E1 was. So they are moving into a new space – sustainable aviation. While Boeing and Airbus are fighting over big jets, Embraer is designing a new generation of green planes. They are working on high-tech turboprops and even electric aircraft under their Energia project. Their strategy is simple. If you can't beat the giants in the jet market, lead the way in the green market. Embraer isn't giving up. They are looking for every gap in the market that the giants have missed. They are betting that the future of flying isn't just about being big. It's about being smart, efficient, and ready to pivot when the world changes. Now I want to ask you, would you prefer the Embraer E2 over Boeing or Airbus? And what do you think about this company in general? I'd be interested to hear your opinion. If you learned something new today, hitting the subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you next time. I found a weird abandoned version B787-3, and it was a real project, by the way. Could you imagine like 757 and 787 had a baby? It's literally what I've accidentally found surfing the internet. It is for sure a weird concept, because just why would you ever need a wide body which can fly only 5,000 miles? So today we will find this out. Actually, the intended range was even shorter. We are talking about a Dreamliner optimized for routes as short as 200 nautical miles. A specialized machine designed to act like a city bus, taking off and landing up to 10 times a day. This wasn't just a paper plane. It has 43 firm orders. It had a completely unique wing structure that looked nothing like the 787 we know today. And it was killed not by a crash, but by the concrete geometry of Japanese airports and the brutal physics of structural weight. In the next 15 minutes, we are going to dig into the hidden specification, the aerodynamic compromises, and the exact economic data that turned this plane into a ghost. But before we open the technical manuals, please hit this like button and subscribe to the channel if you enjoy deep engineering analysis. It helps me a lot. Now let's look at the numbers. Part 1. The anatomy of a mutant. To understand why this plane failed, we first need to understand what it actually was. Because from the outside, the fuselage of the 787-3 was identical to the standard 787-8. Same length, same composite barrel, same passenger capacity. But underneath the skin, it was a completely different animal. Let's look at the hidden numbers. The most critical difference was the MTOW, maximum takeoff weight. The standard 787-8 has an MTOW of roughly 228 tons. The 787-3, it was capped at just 165 tons. That is a 28% reduction. Why would Boeing deliberately cripple their own aircraft? Two reasons: landing fees and structural life. Airport fees are often calculated based on maximum certified weight. Airlines operating 45-minute flights would be paying long-haul prices for short hops. However, notice the MZFW, max zero fuel weight. It remained exactly the same as 161 tons. The 787-3 could carry the exact same heavy payload of passengers and cargo as the long-range version. It just couldn't carry the fuel to get them very far. It was a tank designed to be full of people, but empty of gas. But the real engineering crime, or innovation, depending on how you look at it, was the wing. The standard Dreamliner wing is the masterpiece of aerodynamics. It spans 60.1 meters and features those iconic racked wingtips. These sweep back to reduce drag during high-speed cruise at Mach 85. They are elegant, efficient, and huge. The 787-3 wing was chopped, literally. Boeing engineers reduced the span to 51.7 meters, and because they removed those efficient ranked tips, they had to bolt on massive vertical blended winglets, similar what you see on a 737 or 767. Now let's get into the physics. Why is a shorter wing a problem? It comes down to induced drag defined by this formula. Look at the denominator, b squared. That is your wingspan squared. Mathematically, cutting the wing from 60 meters to 52 meters theoretically increases induced drag by 25 to 30% for the same lift. This is why the 787-3 needed those vertical winglets. They weren't a stylistic choice. They were a necessary aerodynamic crutch, or fence, to stop high-pressure air from curling over the wingtip and destroying the lift efficiency entirely. So we have a heavy wide body with clipped wings, high drag and reduced fuel capacity. Why on earth did Boeing build this Frankenstein? The answer lies in the concrete geometry of two specific airports in Japan. Part 2. The Japanese trap and high cycle hull. The 787-3 wasn't designed strictly for the sky. It was designed for the ground. Specifically the concrete aprons of Tokyo Haneda and Osaka Itami. These aren't just airports. They are high-speed mass transit hubs. In Japan, domestic routes like Tokyo to Sapporo operate with high frequency of a subway line, often seeing 50 widebody flights a day. But there was a physical problem. The domestic terminals in Japan were built around ICAO Code D standards. This code limits aircraft wingspan to exactly 52 meters, the size of a Boeing 767-300 or the Airbus A300. If ANA or GAL tried to park a standard 787-8 with its 60-meter wingspan at these domestic gates, it would cause what is known as wingtip overlap. Essentially, one Dreamliner would block the gates on either side of it, creating dead zones. In an airport running at 99% capacity, losing two gates just to park one plane is an operational disaster. This is why the 787-3's wings were clipped to that magic number, 51.7 meters. It was the maximum amount of airplane you could physically fit into the parking slot. But filling into the gate was only half the battle. The mission profile was the other half. A standard long-haul aircraft flies for 12 hours, lands and resets. It performs one flight cycle per day. The 787-3 was built for high cycle operations. We are talking about flight times of 45 to 90 minutes, with turnarounds of just 30 minutes. It was expected to perform 8 to 10 takeoffs and landings every single day. This brutally accelerates wear and tear. To survive this, the 787-3 requires specific engineering changes that most people missed. First, the engines. It used the General Electric NX-1B54. Notice the number 54. This indicates a thrust rating of 53,000 pounds. The standard 787 engines produced 64 to 70,000 pounds. Boeing and General Electric deliberately derated the engines by roughly 16%. Why? Because in a high cycle environment, the enemy is heat. By limiting the max thrust via software, they lowered the turbine entry temperature, TET. This meant the internal turbine blades wouldn't melt or degrade as fast during those 10 daily takeoffs, significantly extending the engine's life between overhauls. Second, The brakes. Traditional hydraulic brakes get incredibly hot during landings and require cooling fans or long wait times before the plane can push back again. The 787 introduced electric brakes. These were a game changer for the 3 variant. They offered better thermal dissipation and allowed the aircraft to land, unload, load, and taxi out again without waiting for the brakes to cool down. It was the perfect machine for the perfect niche. A wide-body shuttle bus optimized for the unique constraints of Japan. So, with a perfect design and 43 orders from ANA and JAL, why did it die? The answer lies in what engineers call the terrible teens. Part 3. The economics of failure. The 787-3 didn't fail because of a design flaw. It failed because of obesity. In the aviation history, the first batch of 787s produced, line numbers 1 through 20, are infamously known as the terrible teens. Due to early struggles with manufacturing carbon fiber on such a massive scale, this aircraft came off the assembly line significantly overweight. Reports indicate these early frames were between 2.3 and 6.8 metric tons heavier than their target weight. For the long-haul 787-8, this weight penalty was a nuance. It meant the airline just had to carry a little less cargo or fly significantly shorter routes. It was manageable. But for the 787-3, this was a death sentence. Remember, the 787-3 used the exact same fuselage structure. It inherited all that excess structural weight. On a 10-hour flight, the fuel efficiency of the 787's engines eventually pays off. But on a 45-minute hop, you are spending the entire flight burning fuel just to lift the heavy composite structure into the air, only to land immediately. The composite advantage completely evaporated. Let's look at the CASM, cost per available seat mile. This is the only number that matters to an airline CEO. When analysts run the numbers of a heavy 787-3 against a mature, cheap-to-buy Airbus A330-300, the 787-3 offered perhaps 8 to 10% better fuel efficiency on short routes. But its ownership, costs, the monthly lease payments, and insurance for a brand new high-tech jet were nearly 30% higher than the older Airbus. For a regional carrier, the small fuel saving could never pay the massive price tag of the plane. Then the timeline collapsed. The entire Dreamliner program was years behind schedule. Japan Airlines, one of the 2 key customers, entered bankruptcy protection in 2010. They needed a reliable airplanes immediately, not experimental prototypes that were overweight and years late. They realized the standard 787-8, while not optimized for their gates, was at least going to be built. They converted their orders to the long-haul version. With the Japanese anchor customers gone, Boeing looked around for other buyers. British Airways for Heathrow, United for US hubs, they all said no. The capital cost was simply too high for a short-range plane. In December 2010, Boeing quietly removed the 787-3 from its price list. The project was dead. But here is the twist. Today, 15 years later, the weight problems are fixed. The 787 is lighter, stronger, and better. So, could the 787-3 actually work now? Part 4. Revival and the what-if scenario. With the 787 program now mature and the weight issues long gone, could Boeing bring this plane back today? Technically, yes. In fact, if they built a 787-3X, today it would be a beast. We now have the technology that was considered science fiction in 2004. Folding wingtips. Instead of chopping the wing and destroying the aerodynamics, a modern 787-3 could simply fold its tips. It would have the full efficient 60-meter span in the air to save fuel, and then fold to 52 meters on the ground to fit into the tight gates at Haneda or Heathrow. It solves every problem the original had. But it will never happen. And the reason isn't technical, it is the rise of the super narrow body. Since 2010, the market has fundamentally shifted. Aircraft like the Airbus A321neo and the Boeing 737 MAX 10 have changed the mass. These are single-aisle planes that can now carry up to 240 passengers. Compare the economics. To fly a wide-body 787-3 on a short route, you are dragging a massive heavy fuselage designed for 2 aisles and cargo containers that you might not even feel. To fly a 737 MAX 10 on the same route, you carry almost 80% of the same passenger load, but with a trip cost that is roughly 40% lower. The efficiency of modern narrow bodies has cannibalized the market for short-range widebodies. Unless an airport is so incredibly slot constrained that you need to squeeze every single human possible into one departure slot, the widebody just doesn't make financial sense. The niche that the 787-3 tried to fill simply doesn't exist anymore. The Boeing 787-3 remains one of aviation's most fascinating what-ifs. It was a scalpel designed for a very specific surgery, but between the manufacturing delays, the weight penalties, and the shift in market, the patient died before the surgery could even begin. Its legacy, however, lives on. The high-cycle engines and electric brakes developed for this ghost plane are now standard on the 787-10, which ANA and United use today as the spiritual successor to the plane that never was. The 787-3 proved that in aviation you can't just fight gravity, you also have to fight the accounting department. And usually, the accountants win. Thanks for watching. If you enjoyed this deep dive, press the like and subscribe button. Fly safe and see you in the next one. Picture this. You are standing on a tarmac and right in front of you is a machine so impossibly massive that you could literally pack the entire fuselage of a Boeing 737 inside its outer shell, with room to spare. We are talking about a machine that breathes in tons of air every single second, squeezes it with 60 times the pressure of our atmosphere, and burns it at temperatures that would effortlessly melt ordinary steel. This is the GE9X. It is undisputed heavyweight champion of the skies, built specifically for the Boeing 777X. But the story of this engine isn't just about making things bigger. It's about a crazy paradox where the world's most powerful engine actually uses less brute force in its daily life than its predecessor. It's about custom-engineered pixie dust, 3D printing metal, and pushing the literal laws of thermodynamics on the absolute edge. Before we tear into the guts of this absolute monster, if you enjoy deep dives into the bleeding edge of aviation technology, do me a huge favor. Hit that like button and make sure you are subscribed. It takes just a second, but it really helps push these discussions out to more people. So let's talk about the sheer scale of this thing.
because numbers on a screen really don't do it justice. The front fan alone measures 134 inches across. That is almost 11.5 feet of just fan blades. Once you wrap the nacelle, that's the outer housing, around it, the total width comes out to 184 inches. Like I said, a standard Boeing 737 fuselage is only about 148 inches wide. You could slide a 737 right through the engine pod of a G9X. But here is where it hits out first really fascinating paradox. Because it's so huge, everyone naturally assumes it just blasts out more thrust than anything else in the sky, all day, every day. And technically, yes, it holds the Guinness World Record. Back in November 2017, on a test stand in Peebles, Ohio, GE engineers pushed this thing to a staggering 134,300 pounds of force. To put that in perspective, the fighter jets you see breaking the sound barrier usually max out around 30,000 to 40,000 pounds of thrust. The G9X crushed the previous world record, which was held by its older brother, the G90. But if you look at the actual certification documents for daily commercial flying, the G9X is only certified to operate at 110,000 pounds of thrust. The older G90 actually operates at over 115,000. Why? Why build the biggest, most powerful engine in human history, only to throttle it back for everyday use? The answer is efficiency. The Boeing 777X is a highly aerodynamic aircraft with a massive glider-like wingspan. It doesn't actually need to muscle its way through the air with brute force like older jets. By building a larger fan but running it at a slightly lower thrust rating, GE dramatically increased the bypass ratio. Let's break down what that means. Because bypass ratio is the secret sauce of modern jet engines. The G9X has a bypass ratio of 10 to 1. That means for every 1 unit of air that goes into the fiery core of the engine to be compressed and ignite, 10 units of air bypass the core entirely. They are just pushed around the outside of that giant 134-inch fan. That bypass air provides the vast majority of the thrust. And because there is so much bypass air, it creates this massive, relatively cool stream of air that wraps around the superheated, supersonic exhaust shooting out of the core. That shield of air actually acts as a muffler. So despite being the largest engine ever built, GE officially stated that per pound of thrust, the G9X is the quietest engine they have ever produced. Now, moving that much air requires a very special type of a fan. If you look closely at the front of the G9X, you'll notice it only has 16 fan blades. You would think a bigger engine needs more blades, but aerodynamics is a funny thing. Fewer blades mean less weight and less aerodynamic drag. But to make 16 blades do the work of 22, they have to be incredibly wide and perfectly shaped. These blades are made of 4th generation carbon fiber composites. They are incredibly stiff, but pure carbon fiber has a problem. It can be brittle. If a large bird strikes a purely carbon fiber blade at 500 miles an hour, it could shatter. So GE engineers added steel leading edges to slide through the air and deflect impacts. And they used fiberglass for the trailing edges to give the blade just enough flexibility to absorb a shock without snapping. But getting this massive fan off the ground presented a massive headache before the engine ever even made it to a Boeing aircraft. Whenever a company builds a new engine, they have to fly it on a testbed plane first. General Electric usually uses a heavily modified Boeing 747. But when they wheeled the G9X out to their 747-100 test plane, they realized the engine was so ridiculously big that it would literally scrapple the runway. They had to upgrade their test bed to a Boeing 747-400, which sits slightly higher. Even then, Boeing had to engineer a completely custom pylon to attach it to the wing, and they had to tilt the entire G9X upward by 5 degrees compared to the other 3 engines on the plane, just to give it enough ground clearance during takeoff and landing. Imagine looking out the window of a 747 and seeing one engine that is twice the size of the others, tilted slightly toward the sky. That is what it took just to test this thing. Once the air gets past the giant fan, we enter the core, and this is why the G9X sounds like the pure science fiction. To get the maximum amount of energy out of a drop of jet fuel, you have to squeeze the air as tightly as possible before you ignite it. The G9X has an overall pressure ratio of 60:1. The air entering the combustion chamber is compressed to 60 times the pressure of the outside atmosphere. It is violently squeezed through an 11-stage high-pressure compressor. By the time fuel is injected, the air is practically a solid wall of energy. But when you squeeze air that tight and burn it that efficiently, you generate an ungodly amount of heat. The inside of the G9X reaches temperatures of 2400 degrees of Fahrenheit. That is roughly 1315 degrees Celsius. Normally, engineers solve this by bleeding off some of the cool air from the compressor and channeling it through tiny holes in the turbine blades to keep them from melting. But bleeding off air means you lose efficiency. So GE completely changed the materials. They heavily utilized ceramic matrix composites, or CMCs, in the hottest part of the engine. CMCs are made of silicon carbide ceramic fibers embedded in a ceramic resin. They are 1/3 the weight of metal, twice as strong, and most importantly, they can brush off 2400 degree heat without breaking a sweat. Because they can handle the heat natively, the engine needs 20% less cooling air. That air stays in the main flow path, generating more thrust and burning less fuel. And it's not just ceramics. The G9X represents a massive shift in how engines are physically manufactured. It features over 250 parts that are additively manufactured. That's a fancy way of saying 3D printed. But we aren't talking about desktop plastic printers. We are talking about electron beam melting, where a high-powered beam fuses layers of titanium aluminate powder micron by micron. The low-pressure turbine blades are 3D printed. The fuel nozzles are 3D printed. By printing these parts, engineers can design complex internal cooling channels that are physically impossible to cast or forge using traditional metalworking. And because they are printed as a single piece, there are fewer welds, fewer joints, and less weight. But none of this high-tech wizardry matters if the engine breaks down in the real world. And the real world is incredibly harsh. A huge portion of the orders for the Boeing 777X are coming from Middle Eastern airlines, like Emirates and Qatar Airways. These planes are going to be spending thousands of hours flying over expansive deserts, sucking in fine sand and dust. If sand gets into a 2400 degree engine core, it melts into glass, clogs the cooling holes, and destroys the engine. GE couldn't just wait and see what would happen, so they went to extreme lengths. They literally hired PhD-level geologists to analyze the exact chemical makeup and consistency of the airborne dust found at cruising altitudes over the Middle East. It's incredibly fine, almost like talcum powder. Back at their testing facility in Ohio, they built a bespoke rig that blasted this custom engineering dirt directly into the core of a running G9X for thousands of simulated flight cycles. They intentionally tried to choke their own masterpiece to death, just to prove that the 3D printed nozzles and the CMC components could survive the harshest environments on the Earth. When you put all of this together, the 134-inch fan, the 10:1 bypass ratio, the 60:1 pressure ratio, the 3D printed titanium, and the ceramic composites, You get an engine that is a full 10% more fuel efficient than the G90, while producing 50% fewer NOx emissions than current regulations require. The G9X isn't just a bigger engine, it is a fundamental shift in how we move massive amount of weight through the air. As the Boeing 777X finally gears up to enter commercial service, it is going to be riding on the back of an engineering marvel that redefines what is possible in modern aviation. If you made it this far, I really hope you enjoyed this deep dive into the mechanics of the G9X. Let me know down in the comments what part of this engine blows your mind the most. Is it the 3D printing, the size of the fan, or that crazy pixie dust test? And of course, if you haven't already, please drop a like on the video and subscribe to the channel, so you don't miss our next deep dive into the machines that connect our world. Thanks for hanging out, and I'll see you in the next one.
Take a close look at this image. To most people, this looks like a pilot's worst nightmare. But to an engineer, this is a masterpiece. This is a triumph of design. On September 3, 2025, something incredible happened. In a single day, two different business jets, a Gulfstream G150 in Chicago and Challenger 300 in Boca Raton, overran the runway. Both planes were heavy, moving fast and running out of pavement. Both should have ended up in a highway or a building. But they didn't! They stopped safely, the passengers walked away, and the planes didn't even catch fire. They were saved by a technology that hides in plain sight at the end of the runway. EMAS, the Engineered Materials Arresting System. Today we are going to look at the hidden engineering that keeps you alive when a landing goes wrong. But first hit the like and subscribe button. This simple action is vital for me. Thank you very much. The science of soft concrete. So what actually is a mass? If you look at the end of a runway, it looks like a normal extension of the pavement. But it is not. It is a trap. The secret lies in the material itself. This is made of cellular cement, also known as format concrete. Imagine a block of concrete, but instead of being solid, it is filled with millions of tiny air bubbles, like a honeycomb. The engineering brilliance here is not about strength, it is about weakness. Normal concrete, the kind you walk on, is incredibly strong. It can withstand pressure of 4,000 psi, pounds per square inch. If a plane hits that, the landing gear snaps. But EMAS blocks are engineered to be weak. They have a specific crush strength of only 30 to 50 psi. Compare 4,000 to 30 or 50. This number is very precise. It is strong enough to support the weight of a fire truck or a maintenance vehicle without braking. But the moment the thin tires of a heavy jet hit the blocks, the material gives up. It crushes instantly. Part 2. The physics of arrestment. When a plane enters the EMAS bed, the tires slice through the material like a knife through dry foam. The wheels sink into the bed. This creates drag. The material absorbs the kinetic energy of the moving aircraft and converts it into mechanical crushing work. It acts like a giant brake pad made of stone. The system is designed to stop a critical aircraft, usually a heavy jet, entering the bed at speeds up to 70 knots, about 130 km per hour. And the most important part, it does this smoothly. The bed is usually built as a ramp. It starts shallow, maybe just a few inches deep, and gets deeper towards the end, sometimes up to 30 inches. This slows the plane down progressively, so the passengers don't feel a violent impact. Part 3. The problem when space runs out.
Why do we need this expensive technology? Why not just make the runway longer? The Federal Aviation Administration, FAA, has a strict rule. Every runway must have a safety net. This is called the RSA, or Runway Safety Area. The standard RSA must extend 1,000 feet, about 300 meters, beyond the end of the runway. This is a flat, empty, grassy area where a plane can roll safely if it fails to stop. But look at the map. Many airports are built 50 or 60 years ago. Since then, cities have grown around them. Some airports end at the edge of a cliff. Others end at a busy 6-lane highway. Some, like LaGuardia or San Francisco, end directly in the ocean. And these places you cannot just add land. It is physically impossible or financially ruinous. Part 4. The economic solution. This brings us to the economics of safety. Let's look at the real example. Greenville Downtown Airport. They had a steep drop-off at the end of their runway. To build a traditional 1,000-foot safety area, they would have to build a massive earth embankment. The estimated cost was $16 million. Instead, they installed an Immerse. Because the material stops planes so efficiently, you don't need 1,000 feet. You can do the same job in a much shorter distance. The cost of the Immerse? $1.8 million. Compare one more time. 1.8 to $16 million. It saved the airport $14 million. And it provides the exact same level of safety. Part 5. A history of safes. This is not theoretical. This technology has a proven record called tombstone technology. Solution born from past accidents, but now saving lives. Since the first successful safe of a Saab 340 at JFK Airport in 1999, Immerse has stopped dozens of aircraft. In Charleston, West Virginia, a CRJ-200 regional jet aborted its takeoff. The runway ended at a steep mountainside. The Immerse caught it just in time. In Tattleboro, a Gulfstream 4 was stopped before it could cross a busy highway. And of course, the events of September 2025. 2 jets, 2 wet runways, 2 potential tragedies, 0 fatalities. But Immerse is only the last resort. Ideally, we never want to use it. To understand how we keep planes on the runway, we have to look deeper. We need to look at the invisible battle happening between the tire and the pavement. And it all starts with a formula from NASA. Part 6. The physics of touchdown. The most dangerous enemy of a landing aircraft is not wind, and it is not pilot error. It is water. When a plane lands, it is not just rolling. It is fighting a aerodynamic battle. If the water on the runway is deeper than just 3 millimeters, 0.1 inches, a phenomenon called dynamic hydroplaning begins. The water builds up pressure in front of the moving tire. It forms a wedge that physically lifts the rubber off the concrete. In the 1960s, engineers at NASA's Langley Research Center, they found that the speed at which you lose control depends on only one variable. It doesn't matter how heavy the airplane is. It doesn't matter how skilled the pilot is. The only thing that matters is the tire pressure. They created a formula that is still the Bible of aviation safety. Vp equals 9 square root of P. Here, Vp is the hydroplaning speed in knots, and P is the tire pressure in psi. Let's look at the numbers. A commercial airliner like a Boeing 777 has very high tire pressure, around 200 psi. According to the formula, it will hydroplane at about 127 knots. That is fast, but it is usually below the landing speed, so the risk is manageable. its tires are only inflated to 36 psi. The formula tells us it will lose control at just 54 knots. This means a small plane is actually more likely to hydroplane than a massive jet. Part 7. Reverted rubber, the steam seal. But there is a type of hydroplaning that is even scarier. It is called reverted rubber hydroplaning. This happens when a pilot locks the wheels on a wet runway. The friction generates insane heat. This heat boils the water trapped under the tire, turning it into high-pressure stream. The steam gets so hot that it melts the rubber on the tire, rewetting it back to its raw, sticky, uncured state. The result is a disaster. The melted rubber forms a seal around the steam, creating a cushion. The aircraft is now literally riding on a pocket of superheated stream. Investigators know when this happens. They find telltale signs on the runway. White marks that look like the power mount has been stream cleaned, alongside patches of melted rubber. Part 8. Engineering the surface. Grooving. So how do engineers fight this? We cannot stop it from raining, so we change the ground itself. If you look closely at the major runway, you will see it is not smooth. This is called grooving. Engineers cut thousands of channels across the runway. The FAA has a very strict standard for this geometry. The groovers are 1/4 inch 6 mm deep. They are 1/4 inch 6 mm wide. And they are spaced exactly 1.5 inches 38 mm apart. These tiny channels give the water an escape route. It flows into the groovers and drains away, allowing the tire to grip the length, the high points between the cuts. This simple geometric pattern can increase friction on wet pavement by up to 300%. But maintaining this is a nightmare. Every time a heavy jet lands, the tires spin up from 0 to 140 knots in an instant. This abrasion rubs off about 1.5 to 2 pounds of rubber onto the runway. Over time, this rubber fills the groovers. If 40% of the groovers are blocked, the runway becomes dangerous. That is when maintenance crews come in with ultra-high pressure water blasters, shooting water at 40,000 psi to strip the rubber off without destroying the concrete. Part 9. The layer cake. Hidden structure. Now let's go deeper. Literally. Passengers think a runway is just a road, but a highway is designed for trucks. A runway has to survive a 300-ton machine slamming into it at 250 km/h. If you sliced a runway in half, you would see it is a massive engineering layer cake, more than 2.5 meters thick. Look at the cross-section. At the very top you have the surface course. This is the asphalt or concrete we see. Below that is base course, often made of cement-treated aggregate. Then the subbase, and finally the subgrade, the native soil. In major international airports, the top layer alone can be 22 inches, 56 centimeters, of solid Portland cement concrete. This is thicker than the walls of a military bunker. This structure is designed to distribute the massive points of load of a single wheel. If the layers were not there, the landing gear would punch through the pavement and sink into the dirt. Part 10. The evolution of design. For decades, engineers designed these layers using old charts and tables called the ACN-PCN system. It was based on empirical data from the 1950s. But modern aircraft gear is too complex for simple charts. In July 2020, the Aviation world switched to a new standard, ACR-PCR. This is a mechanic approach. Engineers now use computer simulations, called layered elastic analysis. They model the runway as a multi-layered elastic system in a digital environment. They can predict exactly how the pavement will bend and rebound under every single wheel of an Airbus A380. Part 11. The chemistry of asphalt. Finally, even the asphalt itself is high-tech chemistry. It is not just tar and rocks. Engineers use a performance grading (PG) system to design the binder. In a hot climate like Dubai, they might use PG 7622. The 76 means the asphalt won't melt or rot until it reaches 76 degrees Celsius. To achieve this, they modify the bitumen with polymers like CBS. It is basically turns the road into a very stiff rubber band. In a cold climate like Alaska, they use PG 5234. The 34 means it stays flexible down to minus 34 degrees Celsius, so it won't crack in the winter. We built the ground to match the sky, but even the best pavement is useless if the pilot can't see where to land. That is where the engineering of light comes in. Part 12. Tombstone technology. There is a dark saying in aviation: regulations are written in blood. Engineers call this tombstone technology. It means that many of the safety features we see today were invented only after specific disaster. Take the tragedy of American Airlines Flight 1420. In 1999, an MD-82 jet overran the runway in Little Rock, Arkansas. It didn't stop in the grass. It collided with a rigid steel walkway that supported the approach lights. The steel structure didn't break. Instead, it tore the aircraft apart. That accident forced a critical change in engineering. It is called fungibility. Today, strict FAA rules state that any object located in the runway safety area, whether it is a light pole, a sign, or a navigation antenna, must be fungible. This means it is engineered to be brittle. It is strong enough to stand up to a storm, but designed to snap, buckle, or yield instantly if an aircraft hits it. The object must die, so the passengers can live. We see this pattern everywhere. After the collision of two Boeing 747s in Tenerife in 1977, airports were required to install ground radar (ASDE) to see through fog. After the crash of Singapore Airlines Flight 006 in 2000, where a pilot turned onto a closed runway by mistake, lighting standards changed. Now taxiway lights must be physically locked out so they never lead a pilot to a closed runway. Part 13. The language of light. But the best safety system is one that prevents the accident before it happens. This brings us to engineering of light. When a pilot approaches a runway, they don't just guess their altitude. They look for a box of 4 lights on the left side of the runway, the precision approach patch indicator. It looks simple, but the optics are incredibly precise. The system is calibrated to define a perfect 3-degree glide path. Each light unit projects a split beam. The top half is white and the bottom half is red. The transition between the two colors is razor sharp, less than 3 minutes of arc. This creates a simple code for the pilot. 4 white lights, you are too high, more than 3.5 degrees. 4 red lights, you are too low, less than 2.5 degrees. This is dangerous, you might hit terrain. 2 red and 2 white, you are perfectly on the 3-degree path. Part 14. The runway is talking. Once the wheel touches the ground, the engineering shifts from guidance to distance. At night, a pilot cannot easily see how much pavement is left, so the runway talks to them using color codes mandated by the FAA. The centerline lights, the lights running down the middle of the runway, are not just white. When there are 3000 feet remaining, the lights starts alternating red and white. This is the first warning. In the final 1000 feet, the center line turns solid red. This tells the pilot, "You are running out of space. Stop now." Even the edge of lights participate. In the last 2000 feet, or half the runway length, the white edge lights turn yellow. This creates a visual caution zone for the pilots. Now I'm serious. Which part of this hidden engineering surprised you the most? Was it the soft concrete of Immerse, or the fact that NASA formulas control your landing? Write your thoughts below. I read every comment. If you learned something new today, hitting the like and subscribe button is the best way to support me. As a new channel, every subscriber truly counts and motivates me to create better stories. Click here to watch the next video. Thanks for watching and see you in the sky! Imagine an aircraft that literally every major airline in the world was begging to buy. A plane so perfectly designed that it could revolutionize how we fly, cutting ticket prices, unlocking hundreds of new direct routes, and completely changing the economics of the airline industry. It was the absolute perfect machine. Sounds amazing, right? Well, there's just one massive problem. It doesn't exist. And honestly, it probably never will. Today we're talking about the ultimate ghost of the aviation industry. A plane that has been obsessed over boardrooms and aviation forums for nearly a decade. The Boeing 797. Was it really the perfect aircraft? And if it was so perfect, why can't you buy a ticket on one today? Before we dive into the secret engineering, make sure you hit that like button and subscribe to the channel. It takes just a second, but it really helps push these aviation deep dives out to more people. Alright, let's get into it. To understand why the 797 was considered perfect, we first have to understand the massive headache that airlines have been dealing with for the last 15 years. In the aviation world, there is a legendary dead zone called the middle of the market, or the MOM. For decades, this gap was filled by two legendary Boeing aircraft, the 757 and the 767. The 757 was this incredibly overpowered, long, single-aisle rocket ship that could take off from short runways and cross the Atlantic. The 767 was a small, twin-aisle widebody that dominated transcontinental and medium-aisle international flights. But here's the issue. Those planes were designed in the late 70s and 80s. They are aging, they are gas guzzlers by modern standards, and airlines have been retiring them. So airlines desperately needed a replacement. They needed a plane that was bigger and has longer legs than a standard narrow body like a 737 or an A320, but wasn't a massive, heavy and expensive to operate as a widebody like a 787 Dreamliner or an A350. They needed a Goldilocks plane. Not too big, not too small, just right. Enter the 797. Now, just to be precise with the facts here, Boeing never officially called it the 797. Inside the company, this was known as the NMA, the new mid-size airplane. The proposed specs for the NMA were exactly what airlines were dreaming of. The NMA 6X, which would carry about 225 passengers and fly roughly 5,000 nautical miles, and the NMA-7X, a slightly larger version carrying 275 passengers with a range of 4,500 nautical miles. The economics were supposed to be mind-blowing. Boeing targeted a 40% lower trip cost compared to the older widebodies it was replacing, while generating 30% more revenue than existing narrow bodies. It was perfectly designed for long but thin routes. Think about flights from St. Louis to London, or Chicago to secondary cities in Europe, or pushing deep into South America from the US. Routes where you simply can't fill a 300-seat widebody, but you still need the range to cross an ocean. Over 50 airlines, huge players like Delta, United and Qantas, were practically throwing their wallets at Boeing, begging them to build this thing. Qantas even publicly stated they wanted to be the launch customer. But as Boeing dug into the actual engineering, the perfect plane started to reveal some nearly impossible design paradoxes. And this is where the story gets really interesting. Most people just assume the 797 would be a shrunken down 787 Dreamliner, a carbon fiber tube with some new engines. For example, as the 787-3. Have you ever heard of it? By the way, I've created a video about it and it will appear somewhere here. But that wasn't the case at all. Behind closed doors, Boeing realized that a standard wide-body design wouldn't work for the economics they needed. Airlines insisted on the 797 being a twin-aisle aircraft. Why? Because twin aisles mean faster boarding and deplaning times. If you have 250 people cramming onto a single-aisle plane, the turnaround time at the gate is brutal. And airplanes only make money when they are in the air. A 2-3-2 seating layout with two aisles solves that. But there is a catch. Twin-aisle jets typically have massive circular fuselages, which creates a massive cargo holds underneath the passenger floor. Airlines aren't moving that much cargo. They are moving people. So huge circular fuselage just creates unnecessary weight and drag, killing the fuel efficiency. They decided to design an entirely new ovoid or elliptical fuselage. Imagine a shape that is wide at the top to accommodate the two aisles, and the passengers but narrow at the bottom, like a single-aisle jet, to reduce drag and minimize the empty cargo space. It looks brilliant on a blueprint, but in reality, physics hates an oval. When you pressurize an aircraft cabin at 35,000 feet, a perfect circle distributes the stress evenly. An oval creates massive stress concentrations at the curves. Building a pressurized ovoid fuselage, especially out of carbon fiber, is incredibly difficult and notoriously heavy, because you have to reinforce the structure so much to keep it from failing. And that leads us right into the great materials debate. Everyone thought the 797 would be entirely composite, like the 787. But to make this plane perfect, it had to be cheap. Airlines are notoriously frugal, and the market consensus was that to be competitive, Boeing needed to price the 797 somewhere between $65 million and $75 million per unit. To put that into perspective, a 787-8 has a list price of well over $100 million. Building composite barrel sections is exceptionally expensive. To save even more billions in research and development, the 797 was starting to look like a bit of a Frankenstein aircraft. Early renderings and insider leaks showed it would borrow heavily from Boeing's greatest hits. It was slated to feature the massive dreamable cabin windows of the 787. But the cockpit windscreen lineage was lifted straight from the old 757 and 767. The tail cone aerodynamics were derived from the 737 MAX, and the door arrangements mimicked the 767-200. It was a parts bin plane wrapped in a highly experimental oval fuselage. But even if Boeing figured out the shape and the materials, they ran headfirst into the wall they couldn't control: the engines. To make the crazy economics of the 797 work, Boeing needed a revolutionary engine. They needed something in the 45 to 50,000 pounds of thrust class that was 20 to 30% more fuel efficient than current technology. And the brutal truth, nobody had one. Rolls-Royce, General Electric and Pratt & Whitney simply didn't have an engine ready for Boeing's original target launch date of the 2025. Rolls-Royce even formally pulled out the competition for the NMA in 2019, stating their ultra-fun technology just wouldn't be mature enough in time. So, you have incredibly complex, potentially expensive fuselage, missing the engines required to make it fly efficiently, but even then, they might have spent the billions required to make it happen. But then, 2019 happened. The 737 MAX crisis fundamentally alerted the trajectory of the Boeing company. Following the tragic crashes and the subsequent grounding of the entire MAX fleet, Boeing had to pivot absolutely every ounce of its engineering talent, its financial resources, and its regulatory focus toward fixing and recertifying the 737 MAX. The company was bleeding billions of dollars. They simply did not have the capital or the bandwidth to launch a brand new clean sheet aircraft program that would cost upwards of $15 to $25 billion to develop. In January 2020, then CEO Dave Calhoun officially drove the final nail into the coffin. He publicly paused the NMA project, stating that the competitive landscape had changed and Boeing needed to start with a clean sheet of paper. When they were ready, the 797, as we knew it, was that. And while Boeing was fighting fires and posing their perfect plane, Airbus swooped in and practically stole the entire market. Airbus looked at the middle of the market gap and decided not to spend $20 billion inventing a new plane. Instead, they took their existing, highly successful A320 platform and pushed it to its absolute physical limits. The result was the A321 XLR. The XLR is a single-aisle plane. It doesn't have the fast boarding or the spacious comfort of the twin-aisle 797 concept. But you know what it does have? It has a range of 4,700 nautical miles. It carries up to 244 passengers. And most importantly, it actually exists. Airlines that grew tired of waiting for Boeing's perfect paper plane, including massively loyal Boeing customers like United and American Airlines, bought the A321 XLR by the hundreds. It's entering service right now, in the mid-2020s, exactly when the 797 was supposed to dominate. Airbus won the middle of the market without even building a new airplane. So what happens now? Will we ever see a Boeing 797? The short answer is no. Not anytime soon. And certainly not as a twin-aisle ovoid mid-size plane we originally pictured. Fact-checking current statements from Boeing leadership reveals a harsh truth. Boeing will not launch a new clean-sheet aircraft until next-generation propulsion technology, like the open-fan engines, matures. And when the 2030s roll around, the threat isn't just Airbus anymore. A company called JetZero, heavily backed by the US Air Force, is currently building a blended wing-body demonstrator jet. They are targeting a 250 passenger capacity with a 5,000 nautical mile range. Those are the exact specs of the 797. But because of the radical blended wing design, they are promising up to a 50% reduction in fuel burn. By the time Boeing is ready to build their next plane, the entire concept of what a perfect aircraft looks like might have completely changed. The Boeing 797 was an aerodynamic and economic tightrope walk. It was an ambitious, beautiful concept designed for a specific moment in time. But bad timing, corporate crisis and lack of ready engine technology and the brutal reality of physics kept the perfect aircraft locked in the hangar forever. What do you guys think? Should the Boeing have risked it all and built the 797 anyway? Or did Airbus just play the game better with the A321 XLR? Let me know your thoughts down in the comments. If you enjoyed this deep dive into the 797, please make sure to drop a like on the video and subscribe to the channel for more aviation content. It means a lot and helps me keep making these videos.